a little bit about related rates problems, and we've seen that. And last time we've seen that sometimes in such problems you might need some formulas from geometry. Basically something about maybe length of something or volume of something. And I promised that I'll remind you some formulas from geometry which you should know. So let me start. Some formulas about length. Formula that you have a right triangle. When you have a right triangle, the following relation holds: a squared plus b squared is c squared. So, once again, what I'm doing is just I'm reminding some formulas from geometry. I will present no proof, just reminders of the formulas themselves. If you don't know any one of them, just remember it. For a circle, radius r, the length of the perimeter, so the perimeter of the circle, the length of the circle is 2 pi times the radius. For areas, simplest formula is area of rectangle. If the sides are A and B, the area is the product of the sides. For triangle, if you know the height and one of the sides, the area is the side times the height divided by 2. For the circle, radius r, the area is pi r squared. For a sphere, area is 4 pi r squared. Radius is r. So each one of these formulas will potentially be useful in a problem about related rates. For instance, area of a sphere could be, well, you're blowing a bubble and you blow out air at, well, 1 liter per minute. And the question is, how fast is the area of the bubble growing? So then you would obviously need such a formula. What is the area of surface of sphere? For volumes. Once again, there are some simple formulas, like the formula for volume of a box. Volume is the product of the sides. A kind of formula for, well, cylinder, where A is area of the base, and this is height. Volume is height times the area. So a cylinder is just a figure, well, it's a body such that each slice is the same. So the base and the upper base and everything in between is the same thing. Such a picture. In particular, for a circular cylinder, radius of base R, height h. You have the volume is h times pi r squared times h. Maybe another instance of this, if you have a prism and here you have a triangle with height h, this is A, this is B, and this is the triangle with height h. The volume is A, B, H divided by H. So that's basically the same formula. Here, instead of here, the shape of the base is a triangle. The area is A times H over the height is B. So basically the same formula. Squeeze one here, the volume of a ball. Yes, H. H is the height of triangle, so it's such base. That's H. B is the height here, it's the length of this side. So the size of this front rectangle is A times B. This rectangle is A by B, and the triangle by H. Volume of the sphere of radius R is 4/3 pi r cubed, and maybe a cone. So once again, we have a formula for any kind of cone. If the area of the base is A, and the height is H, is area of base. The volume is A times H divided by 3. In particular, for a circular cone, the most obvious one. If this is radius, and this is H, then volume is pi r squared H divided by 3. So you already have seen a problem about this one with the sand pile, and well, basically each one of those can be useful in some problem about related rates. So as I said, if you don't know one of these formulas, well, just look at it and remember it. Most probably, maybe some small exceptions like this one and that one, the most elementary ones. If we are going to give you a problem on a midterm or final exam, they will probably provide the formula. But I can't promise. So to be on the safe side, I just give you the formulas and well, just remember them. Okay, so any questions about the formulas? Any questions? Yeah. Yes, circumference. It's perimeter of circumference. Okay, other questions? Okay, so basically not much to say here. So let's go to the main topic for today, which is about maximum and minimum functions. So eventually we would like to start with a problem, say a problem about a company, about a business, about basically anything, how to minimize costs, how to maximize revenue, how to maximize profits. and we'll write down the function, find its maximum and minimum. For now, we'll just start with any function and investigate how, in general, given the function, to find the maximum and the minimum. And actually, there are some subtle points, so we'll start with analyzing all the kinds of subtleties, and then in the end, we'll consider some examples, and you see that, well, in most examples, it's actually not that hard, but, well, in general, you might expect that some examples might have some subtleties. So I will start with the definition. When we talk about maximum, what do we actually mean by maximum? We say x equal to c in an interval I is a maximum of f on the interval I if very initial condition, the value of the function at the point C is bigger than the value of the function at all other points. And similarly for minimum. But instead we want that the value of the function at the minimum, the smallest value, is smaller or equal than all other values. So, very obvious definition, we say that a point is a maximum of a function if the value at this point is bigger than all other values. If this value is the largest one. And I'm talking about maximum on an interval, so it actually depends on what interval we consider for the function. Let's look at some simple examples. We'll organize this as follows. We'll have a function f interval we'll sketch a small graph of the function and determine maximum and minimum. Let me start with just some of the simplest functions. X squared. I'll start with interval from -1 to 2. So the question is, well, given that the function is x squared, and you want to look at on the interval from -1 to 2, first question, how does it look like? Well, quite obviously, it is a parabola, but it's only part of parabola. Somewhat like this. At -1 the value is 1. At 2 the value is 4. Okay, let's talk about the maximum. What is the maximum value? At what point the maximum is attained? 2, yes, of course. So the largest my function gets is at the point 2, it is equal to 4. For all smaller values, it's clearly smaller. So it decreases from here to here. So here, kind of, 1 could be maximum, but no. It continues to increase all the way up to here, and here it is 4. The minimum, 0, yes. My function is never negative, and at the point 0 it is 0. So that's clearly the smallest one. Okay, let's try same function x squared, but now the interval is from -1 to 1. Same graph, except we draw only part of it, from -1 to 1. What about maximum now? Plus 1 and minus 1. We have not one maximum but two of them. And minimum is still x equal to 0. So this example shows that the maximum can, well, a maximum or a minimum in fact can be not unique. There can be several of them. There's no problem with this. Okay, let's continue. So draw the same table, f, interval, graph. Maximum, minimum. Last kind of obvious example, x squared on the interval from 1 to 2. Now we have such part of the parabola. So just take the interval from 1 to 2. Now obviously the maximum is attained here, x equal to 2, and the minimum is attained on the left edge, x equal to 1. So both maximum and minimum are attained not somewhere inside the interval, but kind of on the endpoints. And you see that actually, well, what is the maximum and what is the minimum clearly depends not only on the function. Quite a bit depends on the interval. So here 1 was the maximum, here it's minimum. Obviously, it really depends on the interval. Okay, let's try less obvious. X squared, but now on this interval. From 1 to 2, the point 1 is excluded. We know how to draw the graph. It's the same graph, but we indicate that point 1 is excluded by small circle. So no problem with the maximum, still x equal to 2 is the largest value. What about the minimum? Okay, so some opinions. Well, we'll have to use the definition. That's why we have the definition. If we are not sure about what is the actual minimum, we must have the actual definition. Well, the definition doesn't allow you to say that the minimum is at the point 1. Just because the definition tells you, we say that the point inside the interval is a minimum if something. This point 1 is not inside the interval. Our interval explicitly excludes this point. So we can't say that it's x equal to 1. We can't also take any point nearby, say x equal to 1.05. Of course not, because even though it is now in the interval, it's not the smallest value. Because we can take even smaller, x 1.0000. So basically, in this case, we can kind of approach the smallest value, but we can never attain it. In this case, we say that there is no minimum. The reason there is no minimum is kind of artificial in this case. The reason is because, well, the point where the minimum should have been attained was, well, artificially removed from considerations. We just excluded the point 1. But still, it can happen. So sometimes there is no minimum. Similarly, we can exclude the maximum as well. If you consider it on an open interval like this, now you excluded both ends, both maximum and minimum. So here you have none, and here you have none. So this definition just tells you how to recognize that a point is a minimum or a maximum. It doesn't tell you that you will always find the maximum or the minimum. Sometimes no. Okay, so it seems that the reason why we don't get a maximum or a minimum is because we actually exclude these points from consideration. But that's not the only possible reason. Let me consider a function. Let me continue here. F interval graph max and minimum. So now my function is like this: f of x. So first the interval. Now I will not exclude any point. I will include all of them. The interval is from -1 to 1, including both endpoints. But my function is like this. It's x when x is non-positive, and 1 minus x when x is positive. Let's sketch the graph. So it's x from -1 to 0, including the point 0. Looks like this. And then it jumps to 1 minus x. 1 minus x looks like this. And at the point 0, the value is 0, not that one. Okay, so let's decide what is the maximum.
What is an open circle?
Open circle, it means that at this point we don't continue this line, but rather we use this definition.
Oh, okay.
Because at the point 0 we should have some value, and the open circle tells you, well, it's not this one.
Oh.
Okay, so what about the maximum? No maximum. Exactly a situation like we had here. So no maximum. It tries to reach the maximum of kind of 1 at the point 0, but it never attains it. Exactly at point 0 you have the value 0 according to the definition of this function. So you never attain this maximum. But there is no problem with minimum. At -1 you have a minimum. So it might look like, well, this function is discontinuous and that's why it has no maximum. Let's try such a function. X when x is strictly negative, and 1 minus x when x is at least 0 on the same interval. It has, of course, the same graph, except now the value at point 0 is not this one, but rather that one. And now we don't have any problem. The largest value of the function is the value at 0, which is 1. So the maximum is attained at the point x equal to 1. And similarly, no problem at 0. X equal to -1 is a minimum. Oh yeah, it's 0. X equal to 0. Thanks. So even though this function is as discontinuous as the previous one, it does have a maximum. So just being discontinuous doesn't prevent the function from having the maximum. And maybe one last example, I'll put it here, but you can put it in the next line. Such function, 1 over 1 plus x squared. And the interval will be from -infinity to infinity. I'll consider all possible values. The graph looks like this. The denominator is always at least 1, and when x is large, it's really large, so 1 over it is very small. So the function looks like this. It becomes almost 0 when x is large, but never actually becomes 0. So the maximum, there is no problem with maximum. X is always, well, x squared is always not negative, so 1 plus x squared is at least 1, 1 over it is at most 1. And the function at point 0 is exactly 1, so here it is the maximal value. But the minimum is never attained. It kind of tries to become 0 when x is very large, it becomes smaller and smaller and smaller, but never actually becomes 0. So once again here we have no minimum. So we see that actually the situation is not, well, that simple. A function might have a maximum and a minimum. Yes, sometimes it happens. A function might have several of them. Also happens. A function might have none of them. Also happens. And it might have none of them for different reasons. Because, well, one of them was actually excluded kind of artificially by not considering an appropriate point. Or the function could be discontinuous, which by the way in itself doesn't prevent it from having a maximum, but it might prevent it. And finally, in this example, kind of the interval is too large. If the interval, I mean, it kind of looks similar to this reason, that we didn't include the endpoints. But here the endpoint is actually at infinity. And we don't talk about the number at infinity. So here it's kind of similar reason for that one, but here we don't, it's not that we artificially exclude the point, it's just we don't have the number in infinity. It's not a number. Well, it turns out that these reasons which we have seen here are actually the only ones which might prevent the function from having a maximum or a minimum. So the reasons are as follows. Removing one of the points from consideration, or the function being not continuous. It turns out it's a theory, which means we can prove it. If f is a continuous function, so if f is continuous on a closed interval, closed means it includes both endpoints. Then it has a maximum and a minimum. So the only reasons which might prevent the function from having a maximum or a minimum are that the interval is not, well, is not closed, doesn't include one of the endpoints, at least one of the endpoints, or the function is not continuous. So here, interval doesn't include endpoint, interval doesn't include endpoint. Here as well, the endpoints at infinity, they are not included. We see the open brackets here. So, same reason, the interval is not closed. Here the function is not continuous. Well, here the function is not continuous, but still has a maximum and minimum, so it could happen that it still has, but it might also happen that it doesn't. So for this reason, we'll only talk about continuous functions on a closed interval. We are not going to talk about discontinuous functions, or if we are going to talk about discontinuous functions, we'll restrict it we restrict them to intervals in which they are continuous. So if we'll talk about, say, such a function, we'll consider it separately on the interval from -1 to 0, and separately from 0 to 1. Yeah.
If a function equals to a constant number, then what's it?
Yes, so if, example, f of x is equal to 1 for all x, and the interval is, say, from 2 to 5, then the maximum any point is 2 to 5, and minimum is the same thing. Any point is 2 to 5. So if the function is constant, then for this function every point is a maximum and every point is a minimum. Once again, using the definition of what is maximum and minimum. The value of any point is at least as big as any other one. So every point is a maximum. Okay. Other questions? Okay. Now, this is about existence. We decided, well, we talked about what might prevent a function from having a maximum, but this doesn't nearly start to answer the question how to find the maximum. Yeah?
For that question, if you use infinity as interval, negative infinity to positive infinity, they will still be maximum at any point, and they'll still be minimum at any point.
Yes.
So it contradicts with his theory, because the
No.
interval of infinity it can't be contained.
Yes. So it doesn't contradict. It still does not contradict the theorem. The theorem tells you if the function is continuous on a closed interval, then it has maximum and minimum.
Right.
It doesn't say that conversely, if the function has maximum and minimum, then it must be continuous and the interval must be closed. No, conversely is wrong. Even in this example, the function is not continuous, but it still has a minimum and still has a maximum.
Okay.
So it's not a contradiction. It's only in one location. Other questions? Okay, so we talked about existence of maximum and minimum. Now let's start talking about how to find maximum and minimum. So first I'll talk about how maximum and minimum look like. So how f behaves near maximum. Well, suppose you have a point where the function has a maximum. What does it mean? It means that the value here is larger than all nearby values. How can it happen? Well, one way is like this. The function increases, then decreases, and everything looks very smoothly. At this point, you must have a horizontal tangent line. If you go to a different color, to show that it's not part of the function. That's one possibility. But that's not the only one. Another kind of possibility. The value here might be larger than all nearby values, but the function is not nice and smooth. It has a corner. Also could happen. And finally, last possibility, we are at an endpoint. Something like this. So we have nowhere to continue. We don't know whether we continue smoothly or not. We just don't have anywhere to continue. We are at the end, at the endpoint. So basically, we have these possibilities. F prime is equal to 0, or F prime does not exist, or endpoint. Yes, that's exactly what we are going to explore. Yeah.
Does f1 exist for the endpoint?
For the endpoint, so usually we talk about, when we talk about endpoint, we just say that f prime does not exist. By our definition of f prime, it was limit as x goes to x naught of something. And it was not one-sided limit, it was both-sided limit.
So it doesn't exist.
It does not exist. Okay, so this behavior, well, it is typical of a maximum, but it does not indicate that you actually have a maximum. Look at such an example. Here you have a point where the behavior is exactly like this. On the other hand, it's clearly not the maximum. So this is not a maximum. Because this is the maximum. Here the value is even larger. So we introduce a separate word for a point which looks like a maximum but is not, well, might or might not be a maximum. We call it a local maximum. If we write the definition, we say x equal to c is a local maximum of f on an interval I if, well, two conditions. One is c is strictly inside the interval. So we don't consider the endpoints to be local maxima or minima. And second, at this point, the value of f is larger than value at nearby points for x close to c. And similarly for minimum. So a local maximum is not about, well, comparing the value of the function to all values. It's only about comparing to nearby values. If at this point the value is larger than just nearby values, that's enough for a local maximum. So at this point, the value here is larger than at these nearby values. So this is a local maximum, only a local maximum. This point is also the local maximum, obviously, but it is also the global maximum. So it's also the absolute maximum. Also absolute maximum. So absolute maximum means, well, the usual maximum. Just at this point, the function is the largest. A local maximum means just its largest among nearby points. And, well, let's look at this picture and label which picture describe local maximum and which don't. So these two, they exactly describe local maximum. These are local maximum. This one is not. So we just explicitly in the definition exclude consideration of the endpoints. We'll consider the endpoints always separate. So for local maximum, local minimum, we want to make sure that the function is, well, that we compare it to both values from the right and from the right. Well, here we made an observation that at the local maximum, where the function looks like this or like this, we also have derivative which is either 0 or does not exist. It's very useful because it's given a function, it's quite easy to find where derivative is 0 or does not exist. Just find the derivative and ask when it is 0 or when it does not exist. So we have a separate word for this. It's called a critical point. We say x equals to c is critical if critical for f on the interval I. If two conditions. One is c is once again strictly inside. The second condition, f prime at the point c does not exist or is 0. So we just give a separate word for this situation. F prime is 0 or f prime does not exist. And what we observed here is that every time we have a local maximum or a local minimum, we also have a critical point. So let me write this as a theorem. If f has a local maximum or a minimum, then well, x equal to c, then x equal to c is a critical point. So at any local maximum or a local minimum, either derivative does not exist, either we have a corner like this, or the derivative is 0. We have a horizontal tangent line. So let's introduce some words, local maximum, local minimum, critical point. Let's combine them into a sentence. Let's look at an example. Let me draw the function. Okay, so here's the function. I, of course, won't give you a formula for such a function. It would be quite a bit complicated, but still, it is a function, some function. And the question is, well, label all the interesting points. Maximum, minimum, local maximum, local minimum, critical points. So let's start. Maybe the simplest one is, well, let's start with global maximum and global minimum. Where is the global maximum? The absolute maximum. At the peak, right, exactly here. At this point, obviously, the value is the largest. It's larger than this here, it's larger than this here. It's obviously the global maximum, absolute maximum. Since we are at this point right now, let's decide whether it's also local maximum and whether it's a critical point. So is it a local maximum? Well, yes, of course. If you look at nearby points, the value nearby is smaller than the value here. Quite obvious. So this is a local maximum as well. And finally, is it a critical point? Yes. The derivative here does not exist. You have a corner. Every time you have a corner, you have a critical point. Okay, let's talk about the minimum. Where is the minimum? Here? No. Right here, in the beginning. Here. So this is the absolute minimum. The value here is smaller than all the rest of the values. But it's not a local minimum. We can't look at a small neighborhood of this point because it doesn't have, well, points to the left of it. So it's an absolute minimum, but it is an endpoint. It's not a local minimum. Endpoint.
Is it critical when you say?
It's not critical. So for a critical point and for a local maximum or minimum, for both we require for the point to be strictly inside the input, which means it's not an endpoint.
Okay. Yeah.
You want to look kind of to both sides of such points. Okay, let's look at local maxima and minima. So local maxima, well, I just tell because it's hard to kind of point out from there. Well, here is obviously a local maxima. It's not global maximum, it's not absolute maximum because the value here is even larger. But at least locally it is a maximum. And it is also a critical point because, well, the tangent line here is horizontal. Well, that's it. There are only two local maximums. This one and that one. Let's look at the local minima. So this one is quite similar to this local maximum. So it's local minimum and the critical point. There is one more, this one. So here I have a local minimum. And once again, it is a critical point. So indeed, like the theorem tells us, every time we have a local maximum or a minimum, it's also a critical point. But did we exhaust all critical points? No, there are more of them. So first kind of critical point is where the derivative does not exist. Where does the derivative not exist? Here, another point. So another corner, but now it's not a local maximum, not a local minimum, just a critical point. The reason is f prime does not exist. Okay, so no other points where derivative does not exist, but there is one more point where the derivative is zero. At least I try to make it zero. Here. So right here the function is decreasing, then it kind of has a plateau, and then it is decreasing once again. So here f prime is equal to 0, so it is a critical point. But for a different reason, f prime is equal to 0. Here you have horizontal tension. So in a way, critical points are, well, if you imagine that this is a mountain and you are a skier, then critical points is where you experience kind of funny moments. Right here you have kind of, well, decrease, then once again, decrease. Here it's even worse. It's, well, you can imagine what happens. Kind of you bump into the ground. Here, well, same situation, and of course, local maxima and local minima, well, obviously they are important. Okay. What is important in this example is that critical points don't have to be local maxima and local minima. So maybe I'll add here explicit mention. Critical does not imply local maximum or minimum. Now we are actually well equipped to take actual functions and decide where they have maximum and minimum. So let's look at examples. Exercise. Find the maximum and minima of f of x, which is x to the fourth minus 2x cubed on the interval from -2 to 1. Well, we'll have to plug in many numbers because there are many numbers between -2 and 1. Okay, so here we have a function. The question is, what is the largest value that this function attains? What is the smallest? So in the future, we'll have a simple algorithm and we'll follow it without thinking much actually. But for the first time, let's slowly and explicitly tell each kind of thought that we have. So first of all, is it guaranteed to have a maximum and a minimum? Well, yes, it is. Because if you look at it, you see it is continuous. And the interval is a closed interval. So we have a theorem that tells, well, the function does have a global maximum and does have a global minimum. So first step is f is continuous on the closed interval so it must have a maximum and a minimum. In the future we will not write down this step explicitly, but we will always actually perform this step. We'll look at the function, decide that it's continuous and that the interval is closed, and then proceed as usual. If it were not continuous, then we would have a problem. Then, well, none of the methods would actually apply. So now it's continuous. We know that there is a maximum, there is a minimum. Let's find it. Well, how to find it? Let's first look at the critical points, because we know that the maximum can occur at a critical point, like here. Let's determine where the critical points are. Okay, very easy. F prime is, well, you can just compute it, 4x cubed minus 6x squared. So first of all, it exists. for any value of x it exists. So we cannot obtain a corner as a critical point, but we might have a point which is critical by having the derivative equal to 0. So f prime of x is equal to 0 if for x squared times 4x minus 6 is equal to 0, i.e. x equal to 0 or x equal to 3 halves. So we got 2 points where the tangent line is horizontal. Derivative is equal to 0. Next, we want to find the global maximum and global minimum. Well, the global maximum or global minimum can occur in 2 ways. One way is also a local maximum or local minimum, or it might be an endpoint. So let's write it down. The global maximum or a minimum must be either at an endpoint or at a local maximum or minimum. Hence, if something is a local maximum or a minimum, it's also a critical point. So we know that the maximum will be attained, well, not anywhere on this interval, but either at one of the endpoints or at a critical point. So we just have to compare 4 different values of my function, the 2 endpoints and the 2 critical points. So compare values of f at the endpoints and the critical points. Let's start with the endpoints. F of negative 2 is negative 2 to the 4th minus 2 times negative 2 to the power 3. So it is 16 minus minus 16, 32. Another endpoint, f at the point 1 is 1 to the 4th minus 2 times 1 cubed, so it's minus 1. I will continue here. Let's continue to the critical points. We have 2 of them, x equal to 0, so we compute f at the point 0. Is 0 to the 4th minus 2 times 0 cubed is 0. And also we have x which is 3 over 2. But I will not compute the value of f at this point. Why not? Why don't I have to compute the value of this point? Yes, exactly. This point is quite irrelevant for me. It's outside my input. So yes, the tangent line to the graph at this point is horizontal at this point. But it doesn't concern me at all. My function, I look at it only on this interval. It does not include this point. So this is outside the interval. From negative 2 to 1. Okay, we are almost done with this question. we know that the global maximum or minimum must be one of these three values. Two endpoints and the critical point which is inside. Which one is the global maximum? This one, of course, we just look at the numbers and whatever is larger is the maximum. So f is x, which is -2. Minimum, well, once again, look at the three numbers, and the smallest one is -1. And if you were to sketch this graph, I mean, the question doesn't ask you, but x, oh, x is +1, yes. So if you were to sketch this graph, I guess I was confused. F is -1. If you were to sketch this graph at -2, you would have a large value, 32. At 0, you would have 0. At x equal to 1, you would have -1. And you also know that at this point you have a horizontal tangent, so something like this. So probably the function is, well, it doesn't have any other local maximum or minimum in this interval, so it doesn't wiggle like this. It is just decreasing all the way to here, and then it has to decrease further. It just has no choice. So it probably looks somewhat like this. I'm not sure, well, how precise this graph is, but it is somewhat precise. If I were to continue this graph beyond the point 1, well, point 3/2, I would have another horizontal tangent, and most probably it would look like a local minimum. I'm not sure. It would have been like this. So either like this or like this. For now, I don't know. So next time we'll talk much more about how to sketch a graph accurately, much more accurate than this one. But even now we do have some information about the graph. Okay, so maybe any questions about this? Okay, let's solve a slightly harder question, and now we'll solve it the way that you would actually write it down, or maybe exam or anywhere. So the new question is f of x is x to the power 2/3 times x minus 5/2. So the question is to find the maximum, the largest and smallest value of the function, maximum and minimum, on this interval from -1 to 5/2. Well, so our solution would be basically similar to the previous one. First step is look at this function and decide whether it's continuous. It's really important because if it's not continuous, well, we'll have to think much more. Let's look at this. There could be a problem with this term, x to the power 2/3. This part is obviously continuous, this one, we'll have to think for a second. So x to the power 2/3 might have a problem when x is 0 or negative. it doesn't have a problem at x equal to 0, because you raise x to a positive power, so it's not like you raise 0 to power minus 5. It's not that you divide by 0, no. You raise it to positive power. And when x is negative, also you don't have any problem, because you take a negative number and raise it to power 2 first. So you make it positive and then extract a cubic root. So there is no problem with this. So f is continuous. And the interval is closed. So it's a good idea to write something short to show that we actually thought about it. Next, we determine the critical points. Yes, the power is good. Well, for critical points, we just compute the derivative and decide when it doesn't exist or when it is 0. So let's look at critical points. F prime of x. Well, we have a product. Let's apply the product. 2/3 x to minus 1/3 times x minus 5/2 plus, I leave the first term as it is, derivative of the second one is 1. So x to the power 2/3. Okay. To find out whether a point is critical, I should find out whether f prime does not exist or is equal to 0. What about the option that it might not exist? Is there some points where the prime does not exist? When x is 0, yes. So this expression doesn't make sense when x is equal to 0. When x is equal to 0, it reads, well, 0 to the power minus 1/3. It's as if you take 0, raise it to the power 1/3, and then divide by x. So it's 1 over 0, because it does not exist. So f prime does not exist when x is equal to 0. So we found one critical point. At point x equal to 0, we will have a coordinate. Other points, f prime of x is equal to 0 when, well, we'll just take this expression and try to make it 0. 2/3 x to minus 1/3 x minus 5/2 plus x to the power 2/3 is equal to 0. So we have to solve it somehow. Maybe let's move this term to the right first. 2/3 x to minus 1/3 x plus 5/2 is minus x to 2/3. Now let me multiply by this term x to the power 1/3. So I'll move this term kind of to the right. X to the power minus x to the power 1. It's 2/3 plus 1/3, which is 1. And now it's easier. Now I open the brackets. 2x plus 5 is equal to minus 3x. So I multiply by 3 and I open the brackets. So x is 5x is minus 5, x is minus 1. Yes,
That should be minus x squared.
minus x squared. Which one? This one? So I believe that no. So it's minus x to the power 2/3 times x to the power 1. So it is x to the power 1, but I did make a mistake, I changed the sign somehow. Here from minus to plus, so this should have been minus, 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 and I guess this is plus, and this is plus. So I did make a mistake, but now I correct it. Okay, so we did some algebra, well, not complicated, but complicated enough for me to make a mistake. And we found out that the other critical point is x equal to 1. So we have two critical points. And now we know what we have to do. To find the global maximum and global minimum, we should just compare the value of f at the critical points and the endpoints. We know that maximum and minimum can be obtained either at the critical point or endpoint. So values of f at, let's start with critical points, say f of 0 is, yes, 0 is a critical point, so it's 0 to the power 2/3 times 0 minus 5 halves, so it's 0. F at the point 1 is 1 to the power 2/3 times 1 minus 5 halves, so it's minus 3 halves. We should remember to compare it to values of f at endpoints. F of minus 1 is minus 1 to the power 2/3 times minus 1 minus 5 halves. So it's minus 7 halves. Minus 1 to the power 2/3 is, well, minus 1 squared is 1. 1 to the power 1/3 is 1. So this is just 1 times minus 7 halves. And f at the point 5 halves is 5 halves to the power 2/3 times 5 halves minus 5 halves. And luckily for us, it's just 0. And all the rest is just compare these four values. So let's determine where is the maximum and where is the minimum. Let's start with the maximum. Where is the maximum? 0. Yes, the maximum is 0. So among these four values, 0 is the largest one. The other two are negative. But it is not attained at one point, it's attained at 2. But it's okay, we might have two different maxima, x equal to 0 or x equal to 5 halves. So in this case, it happens we have two different maxima. And the value of both is of course the same, 0. What about the minimum? Well, each one of those is smallest. Yes, minus 1. So x equal to minus 1. And let's try to sketch this function. Once again, it's not part of the question, but still, it's interesting how it looks like. How is it possible for such a function to have, say, two maxima? Okay, so let's start at the left-hand point, minus 1. The value is minus 7 halves, so it's quite negative. At point 0, it's 0. At point 1, it is minus 3 halves, so negative but not as much. And at point 5 halves, it's 0 once again. Now let's look how to connect these dots. Well, it doesn't have, so the only critical points are this one and that one. So it means, well, from here to here, it doesn't have any once again, any wiggles. It just increases without changing direction. At this point, at 0, the derivative does not exist. So we must have some kind of corner. We don't know how kind of open this corner is. Is it very, very kind of spiky corner or not? But some kind of corner. Okay, from here to here, the value becomes smaller, so the function must decrease. Here we do have a derivative, and it is equal to 0. So it must be something like this. And from here to here, the function is increasing. The value becomes larger. And once again, without any kind of strange things in between. So the function looks like this. Okay, so any questions about this example? Yeah? It's not a straight line. It could be quite different things, but it must be something which is increasing. Okay, so maybe we just write down the algorithm. Guys, we still have 2 minutes. So I mean, I'm not going to start a new example, just summarize. So we have a pretty good algorithm how to find the maximum and the minimum. First step, make sure f is continuous. So once again, if the function is not continuous, nothing works. I mean, we can't really talk about derivative at some points where it is continuous. We can't talk about, basic arrangement. Second step, find critical points. Find compute f prime and find critical points. Here we have kind of 2 steps. F prime does not exist, or F prime is equal to 0. And finally, compare values of F at critical points and the endpoints. So next time we will indeed continue talking about sketching, but for now, well, no. So on the midterm, you are not going to get a question which asks you just find global maximum and minimum. It will be part of another question, most likely a part of sketching question. Sketch a function and then find global maximum and global minimum.